Okay, sorry. Thank you very, very much to have recalled that. Okay. Okay, I don't repeat now, but let's go on with the new exercises and the new sections. Okay. So let M be the incidence matrix and A the adjacency matrix of a graph G. Show that every column sum of M is 2. Why? Let's think of what an edge is. Either it is what is called a link, that is, its ends are different, two different vertices, or it is a loop and its ends coincide in just one vertex, okay? But in the first case, we put a 1 in correspondence of at the intersection of the column corresponding to the link with each of the two rows corresponding to its ends. Okay, so 1 plus 1 is 2 and no more. And if it is a loop, we just have one entry which is different from 0, where in the row corresponding to the vertex, which is the only end of that particular loop. So that every column sum of M is 2 is just by the definition itself. And then there is the question, what are the column sums of A? And of course, you can try to understand what's going on by looking at the examples, but then you must have a general answer. So what do you have? Let's take any column H, and then we go row by row, row 1, row 2, row N, okay? And we have what? The number of edges connecting vertex VH with V1, and then the number of edges joining VH with V2, and so on and so forth for all the vertices. Okay, but an edge, the same edge, of course, connects two vertices or one vertex with itself. Okay, and so it cannot appear in any other rows. Okay, and so what we have is the number of edges. If we sum along a column or along a row, here we have a symmetric matrix. Then we have the number of edges incident to that particular vertex VH. Okay, so we have what we are going finally to call the degree of that vertex. Subgraph, we have gone through this terrible, many things to say, but I'm not interested in hearing you repeat all this stuff. Just if I say G minus E, I want you to know what is that. I mean that I take away edge E and that's all. And if I take away a vertex V, that's a bit different because I take away vertex V and all edges incident to that particular vertex V, and that's more or less all. Union it's not that important. What I want you, this is a difficult one, okay? Find a bipartite graph that is not isomorphic to a subgraph of any K cube. Now, that's not easy. Why? Because K might be any number. It's not saying it's not isomorphic to a subgraph of the 3 cube or even of the 4 cube, of any K cube. So you must not only try to construct a bipartite graph, but also to have, while you build it, to have an idea of showing that it cannot be a part, it cannot be a subgraph of any K cube. So you have to reason in terms of those coordinates, because every vertex you are going to draw in your trials of it's very difficult that you do it from scratch at the first trial, okay? Generally, it requires, but for any mathematician, maybe except Gauss, but almost all mathematicians try, wrong. Some are always wrong, and the lucky ones are right after some months or some years, okay? And so, okay, when you build it or try to build it, you must not only think of the vertices, but the vertices must be thought as k-tuples. What is k? Any. Okay, and you must show that it cannot be isomorphic to a subgraph of any k-cube. That's a very difficult exercise, in my opinion. So again, don't spend more than 15 minutes on it. Oh, finally, vertex degrees. The degree dg of the vertex V is the number of edges incident with V, each loop counting as 2 edges, okay? And it's easy to think of that if you just if you draw the graph and cut a small disk around the vertex, and so you'll see how many that degree, and actually if you have a loop you'll see 2 pieces of the loop near close to the vertex, so it's easy to remember and to look and see the degree of a vertex, okay? And now be careful, because we shall always use throughout the course, use these 2 symbols. This is small delta, small Greek delta, capital Greek delta, small delta and capital delta, and small delta of G is the minimum degree of the graph or the given graph, and capital delta of G is the maximum degree of the vertices, okay? Okay, and here we have a very easy theorem, if you want, which says, but it is a useful one, you'll see, if you sum all the degrees of all vertices, you get twice the number of edges. Okay, epsilon, I recall, is the number of edges in our graph. Okay, here we have a proof. Consider the incidence matrix. Okay, take the sum of the entries of the matrix in the row corresponding to a certain vertex V. Then we have exactly the degree of V. Why? If it is the end of a loop, then we'll have a 2 in correspondence to the column of the edge, which is the loop on it. Okay, and you have a 1 for each link incident to that vertex. So if you sum the entries in one row, you get the degree of the vertex corresponding to that row. Okay, and so if you sum the sums of the rows, what does this mean? It means sum all the entries in the matrix. Okay, but you are summing row by row, you are summing the degree of V1 plus the degree of V2 up to the degree of V, okay? And so you have that if you sum the sums of the rows, you have the sum of the degrees. But the same sum of everything is also the sum of the sums on the columns, okay? So I sum the sum of the column 1, and column 1, what does it have as a sum? 2. It was this, where is it? It was this exercise we have just seen. The sum of each column is 2, and you have a column for each edge, be it a link or a loop. You still have, in any case, you have 2, and so you have what? The sum of everything, which you can think of, sum of the row sums or sum of the column sums, If you think it of the sum of the row sums, you get the sum of all degrees. If you think it the same number as the sum of column sums, you have what? 2 for each edge, and so twice the number of edges, okay? This is nice, and if you already have matrix M, you are done. But I want you also to give you a different way of thinking of that, okay? And it is something I already used when we had another exercise, okay? Let's think that we have a graph representing some handshaking here, okay? And so I hate Italians, and so I will not shake hands with the Italian present, all right? But I shake hands with the two Turkish ones, okay? And but the Turkish fellows have nothing against the Italian students, so they shake hands, okay, but, oh, all right, so we have not the complete graph, but we have a graph of handshaking. And so now I count my handshaking, okay? And so I count, and this is what? It is the degree of me as a vertex. And then the Italian fellow counts his handshakings, which is his degree. The Turkish lady does the same. The Turkish boy does the same. So each one is counting what his or her handshakings, so his or her degree. All right? Now, if we sum all of them, each handshaking has been counted twice. And so this is twice the number of handshaking, that is the number of edges. Okay? So even without matrix M, you can understand that this theorem is actually true. Okay? Let's see a first consequence. In any graph, the number of vertices of odd degree is even. Meaning, you think you have freedom. Why do I like so much graph theory? Graph theory was one of the reasons why I chose mathematics instead of physics, I must confess, okay? And something else, a very beautiful theorem which was striking, okay? But also the fact that I met graph theory. And what I found lovely in graph theory was its incredible freedom. I'm not bound as in Euclidean geometry. Euclidean geometry is so rigid. You must take a straight line, but if you tremble a bit, it's no more a straight line. A circle must be perfectly round, otherwise the theorems are wrong, they don't apply. Okay, graph theory is free, you can, not so free as you might think. Would you try to build a graph which has only one vertex with the odd degree, only 3 vertices with odd degree? You'll never be able. Why? Because of this little theorem. Why? Let's see. The idea is this. Take any graph, okay? And now subdivide the vertex set into 2 sets of vertices. The set of vertices which are of odd degree, the set of vertices which are of even degree. Okay, let's say this odd and this even. Okay. Now, what about this sum? It is a sum of even numbers. How much is it? So what can we say? A sum, take any sum of even natural numbers. Then can it be odd? If I sum even to even, even to even to even, even to even, then it is even. So this is even. This is even because of this theorem. Remember, epsilon is a natural number. It could be 0, okay, but it is a natural number. We rarely, almost never have here decimals, okay? We are dealing almost always with non-negative integers, okay? So this is an even number, this is an even number, and so this must be an even number as well. But this is an unknown sum of odd numbers. Now, if I sum odd to odd, what do I get? Even. If I sum odd to odd to odd, what do I get? Odd. Odd to odd to odd to odd. Even. Odd to odd to odd to odd to odd. Odd. Okay. So this must be, since all numbers which are in this sum are odd, the number of addends, the number of numbers, the number of addends actually must be even, okay? So you get exactly this. The number of vertices of odd degree is necessarily even. You are not as free as you might have thought to be, okay? An important class of graphs is the one of k-regular graphs, where all vertices have the same degree. And if this degree is k, the graph is called k-regular. Okay? Complete graphs are an example of regular graphs, and also complete bipartite graphs with the two sets of the bipartition with the same number of vertices, okay? Also k-cubes are regular, okay? And in particular, if you have a k-cube, each it is a k-regular graph. This is fairly easy, and I leave it to you for next time. But please remind me that I've left it to you. No more than 5 minutes, 3 minutes. Okay, this is easy. Don't forget the meaning: small delta, minimum degree; capital delta, maximum degree in your graph; epsilon, the number of edges; ni, number of vertices. Okay, do it. Oh, I like this very much. Show that in any group of 2 or more people, there are always 2 with exactly the same number of friends inside the group. Okay? Okay. This comes from set theory, actually. And what do they say? If you have a group of 2 or more vertices, if you have a graph with 2 or more vertices, there are always at least 2. 2 here should be said more precisely, at least 2 with the same degree. Okay? And they say that in a more friendly way, okay? But it is, in any graph, you have at least 2 vertices with the same degree. Can you prove it? This comes from another thing. Instant 0 is this. This was instant 0, okay? I claim that at instant 0, there were in the world at least 2 persons, 2 humans, with exactly the same number of hairs on their body. I'm totally sure of it. How can I prove it? The thing is called generally the pigeonhole method. I'll give you another similar thing. Okay.
The name pigeon nest or some pigeonhole, you said?
The pigeonhole meaning where the mailbox of normal mail. Okay, it's called like this. Anyway, take this other problem. Affect our engineering faculty in Bologna has roughly 10,000 students. Okay, I claim that there are at least two engineering students celebrating birthday in the same day. This is a bit easier. How can I do that?
Can also be three.
Pardon me?
If there are 1,000 students, it can be like three in the same day.
Oh, generally many more. Can you prove it?
Yeah, I heard of
It's not
that
a
theory.
matter of probability, yeah?
Nest.
It's not a matter of probability. It's totally sure. Can you prove it?
It's like, for example, if we have 10 nests and 11 pigeons, there is at least one pigeon that is in
Yes, that's yes.
two pigeons in one,
Pigeonhole, pigeon nest. Okay, but can we formalize this?
like k of n plus 1 in a mathematical way.
Yeah, sure. We are in mathematical methods, so we have to prove mathematically that there are at least two engineering students of Bologna celebrating birthday in the same day. How can we do that? Mathematically. No probability. Set theory. Okay, I give you this. Because you all know the idea. Here we are here to transform rough ideas into mathematical reasonings, okay? And so this is nice because it's different from the other one of the bipartite, which is not a subgraph. Everybody here understands why. But now we must transform it into a little theorem. And the idea is this. Let's go to definitions. Definitions are the real key of mathematics. And what is the definition of number n is greater than number m? The definition of this is that if you have a set of n objects, okay, sorry, let's do it the other way around. Number m is less than or equal to number n. What does that mean? How do you define this thing? It is defined in this way. Take a set of m, the small, m objects. Take a set of n objects. M is less than or equal to n if you can build an injective map from the first to the second. If you can build an injective map from set A of m objects to set n of n objects, then m is defined to be less than or equal to n. Okay? So the idea is, what does it mean that 10,000 is more than 365? It means that if we had less students than days in the year, we could assign to each student a different day of the year, and we could build an injective map. Okay, injective meaning that different objects in different objects in the domain are transformed into different objects in the range, in the codomain. Okay, but we know that 10,000 is greater than 365. So if we assign to each student of engineering of Bologna his or her birthday, it is impossible that this is injective. Why? Because we know that 10,000 is greater than or equal to 365, okay? And so it is not possible to build, and this is a map. What is a map? From A to B. A relation which assigns to each element of A exactly one element of B. In our case, A, the set of students of engineering of Bologna. B, the set of days in a year. Okay? The application to each student, his or her birthday. So it is an application. Of course, every student, and let's take also 366, also considering the 29th of February for the ones born in a business style year, okay? All right, anyway, to each student, there is exactly one day in the year assigned, okay? Maybe it's not subjective. Maybe there is a day which is not covered by anyone. We are not interested in that. What we know is that 10,000 is greater than 366, and so it's not possible that our application is injective. So there is at least one element of the codomain which is the image of at least two elements of the domain. And this is a mathematical proof, and not due to not with a probability. Absolutely sure. And in the same way, how many hairs can a human have on his or her body? Okay, let's be excessive. 1 million. I would like to see such a man. Okay, I'm hairy, but I'm very far from 1 million. Anyway, let's take 1 million, but there are 7 billions humans. And so if you assign to each human the number of hairs in instant zero, T0, that is an application. And it cannot be injective. Why? Because 7 billion is more than 1 million. Okay? And so it is impossible to build an injective application from a domain of 7 billion to a codomain of 1 million. 1 million what? 1 million numbers. The number of hair. To me, it will be, I don't know, 150,373. I don't know. That is the number associated to me, which is not my set of hairs. It is the number of hairs. And so the possible numbers are between 0 and 1 million, and they are too few. The codomain is too small for an application having domain of 7 billion to be injective. And so necessarily there were at that moment, at any moment, there are at least two people, and actually many, many more, having exactly the same number of hairs. Again, okay, now you have to apply this pigeonhole principle to this, and okay, do it. This means, given a finite simple graph, here the number of friends means again that we are in a simple graph, okay? Either you are friend with him or you are not, and you have not loops. It's not a matter, not a Freudian thing of being friends of himself, no. Okay, so meaning translated into graph theory, show that in a simple graph there are always at least two vertices with the same degree. Okay? Do that. Do that. Okay? Also in India, Pakistan, Iran, Libya, and Mexico. And China, sorry. Now to something else. And this I want to, no, I don't know, no. I'm tempted to solve it now because I like it so much. No, I leave it for you to solve. Okay, G has vertices V1, V2, Vn. We take the sequence dV1, d of V2, d of Vn. This is called a degree sequence of G, okay? A degree sequence because we could also order these vertices in another way, and so these numbers would be ordered in another way. Show that a sequence of non-negative integers d1, d2, dn is a degree sequence of some graph if and only if this sum is even. So, meaning, be careful, when they say a simple graph, they say it explicitly. So, generally, this can be also a graph with loops and with multiple edges, okay? How can you prove something like that? This is something more for engineers, finally, okay? Because the only proof which I have in my mind is constructive, meaning my solution is you give me a sequence d1, d2, dn such that the sum of all these non-negative integers is even, and I build a graph with exactly that sequence. Not only, but I can program. You see what I mean? I can write the code for building such a graph. In the sense, I build a program such that 1000 integers come in with the sum which is even, and then the program produces a graph with that degree sequence. Okay? This is the only way I know for proving this exercise. So this is my hint. Try a construction, a general construction. And of course, start from something. Start from a simple, a short sequence and try and refine and modify. Okay? And finally, you should have something which, if I give you 1000 such numbers with sum which is even, then your procedure tells me how to build such a graph. Okay? So here the graph is allowed to be with multiple edges, with loops. Okay, now a similar exercise. A sequence d1, d2, dn is said to be graphic if there is now a simple graph with that degree sequence. Okay? Now, show that these two sequences are not graphic. Again, let's do it next time, tomorrow, okay? Tomorrow there will be a student coming for at the beginning of the class showing something about a project, a racing car project of the engineering faculty. Okay, so we'll spend 10-15 minutes for that. After that, we'll solve these problems. So don't wait. You do it this evening, tomorrow morning, but please try at least one, maybe two of these exercises, okay? All right. Now let's go to connection. Again, here we have something which is simple and which has given me, unfortunately, the necessity of rejecting many students for very silly things. Okay. Things in graph theory are generally very intuitive. But here we want them to be absolutely formal. Okay, so a walk. Look at what a nice word for that. A walk in G. You can understand that pretty well. Okay, these are squares, vertices, and you have streets or bridges or whatever you want. And so you walk from one square to another square through a street and to another square. Very, very easy to understand. Now we want to make a formal definition of that. So what is it? A finite non-null sequence, vertex, edge, vertex, edge, vertex, edge, vertex, finally. So V0, E1, V1, E2, V2, E3, and so on and so forth, up to EK, VK, whose terms are alternately vertices and edges. And what is next is forgotten by many students. If I say just that, I could set a vertex here, an edge there, a vertex there, an edge here. No, what we want for such a sequence to be a walk is very easy to say, but we must say it such that for each I between 1 and k, the ends of edge EI are exactly VI minus 1 and VI. Okay, and these can also be the same vertex. So EI might be a loop and VI minus 1, VI be the only end of that loop. But if I pick up any edge, the two vertices which are before and after must be its ends. Tens of students don't tell me this, and they fail immediately. Okay? Can I show you with an example? No. You must give me the correct definition. Okay. We say that W is a walk from V0 to Vk or a V0 Vk walk. The vertices V0 and Vk are called the origin and terminus of W or capital W respectively, and V1, V2, Vk minus 1, its internal vertices, apart from origin and terminus. The other ones are called internal vertices. The integer k is the length of W. If W is equal to V0, E1, V1 up to EK, VK, and W prime starts from VK, goes on with VK plus 1, VK plus 1 up to EL, VL, and these are walks, and you have that the terminus of the first is the origin of the second, then, okay, first of all, you can have a reversed or inverse walk just by reversing the sequence Vk, Ek, Vk minus 1 up to E1, V0. This is denoted by W to the minus 1. And important, you can concatenate, you can build the product of the two walks by concatenating the two. You end with Vk and you go on with Vk, Ek plus 1 and so on. Okay? What is a section of a walk is a walk which is just a subsequence of consecutive terms of W. And we call it VI, Vj section, where Vi and Vj are respectively the first and the last vertex in this subsequence. In a simple graph, a walk is determined by the sequence of vertices. Why? Because between V0 and V1, you can only have one edge or none. And so it's impossible that they are in this situation in a walk, or they are actually adjacent, And so there is exactly one edge because we are talking about a simple graph. So actually the walk is determined just by the sequence of vertices. And if we are in a simple graph, we'll always just write down the sequence of vertices just to write a little bit less without forgetting information. Moreover, even in graphs which are not simple, we shall sometimes refer to a sequence of vertices in which consecutive terms are adjacent as a walk. Okay, it should be understood that the discussion is valid for every walk with that vertex sequence, so that it is indifferent to use one or the other parallel multiple edges between two given vertices. Okay. Walks in which the edges which appear in the sequence are distinct is called a trail. So a trail is a walk with no repetition of edges, okay? But you might have that you go through the same vertex more than once, okay? In this case, the length of the walk is just the number of edges in the walk itself, okay? If in addition the vertices are distinct, what might not be the case in a trail, we call that a path. Okay, here I go through the figure because we must see the different possibilities. A walk could be this: U, A, V, F, Y, again F, and so it's not a trail because we are repeating an edge. V, G, Y, H, W, and B, V. Okay, so we have repeated vertices and edges. So it's a walk. It's surely not a path, but it's not even a trail. This will be a trail. W, C, X, D, Y, H, W. So we are repeating W, okay? So it will not be, it is not a path, but we have not yet repeated edges, and we shall not repeat edges. Okay, so we are here in W, and we go through B to V and through G to Y. Okay, so this is a trail. And finally, we have an example of a path: X, C, W, H, Y, E, U, A, V. Okay, of course, each path is a trail and is a walk. Each trail is a walk. All right. Okay, now another notion which I ask quite frequently, and again here I had to reject many students for such a simple thing. But I know why. Because the notion of being connected is very intuitive, and so you maybe don't take care of reading and understanding a mathematical definition. But this is a course on mathematical methods. So please be very careful with the definitions. Two vertices U and V of G are said to be connected if there is a UV path in G. How can it be simpler than this? Why shouldn't you remember this easy definition? Connection, so being connected, is an equivalence relation on the vertex set V. Why equivalence? Because, okay, you have a zero-length path from U to itself. If you have a path from U to V, you can reverse it, and you have a path from V to U. Okay, and if you have if you have a UV path and you have a VW path, are you sure you have a UW path? We'll talk about this when we look at this exercise 1.6.1. Okay, but I promise that also transitivity is respected. So we have an equivalence relation. Equivalence relations induce a partition. What is a partition? If I have a set V, a partition of V is a family of subsets of V such that any two of them are disjoint and the union of all of them makes the whole set V. Okay? This is a partition. And whenever we have an equivalence relation, then this induces a partition. Okay? So there is a partition of V into non-empty subsets V1, V2, V omega, such that two vertices U and V are connected if and only if both U and V belong to the same set, Vi. The subgraphs induced by these vertex sets are called the components of G. Unfortunately, tens and tens and tens of students were not able to tell me what a component of a graph is. The number of components which will be of use in the next things is called omega of G. So the number of components. So what is a component? Here, this is a graph, and also this is a graph, but it is a non-connected graph, a graph with several components. So, how can we say in another way without talking about equivalence relations? What can we say about components? A component can be seen like this. It is a connected subgraph maximal with respect to this property. I'm sorry, I forgot to make a break, so now I go on up to 1845, okay? And 1845, I swear I stop, okay? Oh, all right. Maximal. This is an important adjective which is different from maximum. We'll have both maximal and maximum. And a component is a maximal connected subgraph. What do I mean by saying maximal? Let me show it by repeating this drawing. Okay, I had what? This, right? Poi quello lì, sì. Okay, so I could take this subgraph. Is it connected, direct subgraph? Is it connected? Meaning, what does connected mean? If I pick up any two vertices, is there a path from one to the other? Red vertices. Answer? Is this a subgraph? Sure. It is a subset of vertices, a subset of edges, and we have the same incidence function. The same edges which were in the black graph are joining the same vertices also in the red one. So it's a subgraph. Is it the red subgraph? Is it connected? Yes. Why? Because if I pick up any two vertices, there is a path joining them. This and itself, yes, a zero length path. This and this, sure, a one length path. This and this, sure, a two length path. Okay, this and this, and so on. Okay, this is a connected subgraph. Is it maximal? Meaning, is there a another subgraph of G? Okay, let's go. Sorry. Just a moment. All this is graph G. Tell me. Tell me. You had a question? No. She didn't have a question. Okay, this is graph G. Okay, this is a subgraph which is connected. Is there a subgraph of G which contains the red subgraph, a connected subgraph of G which contains the red subgraph? I have an answer, no. I have to make notations with a few electors. The lady says, is there in G a subgraph of G, a connected subgraph of G, containing the red one as a subgraph? You say yes, and so 2 to 1 for yes, and yes is the correct answer. If I pick up this green subgraph, it is also connected and contains the red one. Okay, so the red one is connected, but it's not maximal with respect to connectedness. Why? Because there is another connected subgraph of G containing it properly. The green one is a component. Why? Because it is a connected subgraph of G, and there is no connected subgraph of G containing it. Analogously, this is a connected subgraph of G, okay? But it is not a component, okay? Why? Because there is a connected subgraph of G containing it. This green one, this is another component. And look, also this is a component by itself. So, of course, it's all easy to look, okay? And I know very well that anybody, but also my granddaughter Agatha would say that this is a piece, this is a piece, and this is a piece. Yeah, but my granddaughter Agatha is 5 years old. I want some engineers, some graduate students to be able to give a formal definition. A component, if you want, is an equivalence class of the relation being connected, or if you prefer, I like this in particular, it is a maximal connected subgraph of G. If you have doubts, tell me. Today, better yet, tomorrow. Okay, if you have doubts, ask me. Ask me, please, before the exam. I don't want to explain to you these trivial things at the exam, because this means wasting time, you and me. Okay, now let's go to this, okay, 1830. This problem. Again, this is intuitively rather easy, but we must be able to do a formal proof of this. So that if there is a UV walk in G, then there is also a UV path in G, without repetition of vertices. How can we do that? I go a priority to the outside students. Anybody with an idea? I have a UV walk. I'll give you a verb which helps. How can I extract a UV path from it? Can I make an example? No. Make an example for yourself. Of course, every mathematician, I have said that already quite a lot of times, all mathematicians work with examples. for going up to a general formulation of the solution of the problem, of the theorem. This is mathematics, okay? Otherwise, it's kindergarten. Okay, let's start with an example. Let's do something like this. We have then U. Let's put another one. And we have V, okay. And then I have a path. I'll give names to the edges while I go.
Excuse me, Professor. Can we say that if there is a work inside the graph, there is a simple subgraph that has a path? Like if we are considering a simple subgraph, then...
we start from a simple graph anyway.
Okay.
Let's start with the simple graph. The problem is still there, okay? But let's see with an example how we can gather ideas. Okay, I make a walk. E1. E2. E3. E4. E5. E6. E7. Okay. Now, what can I say? Okay, I have here that going and coming back. So this is actually a trail, doesn't matter. But it's not a path because of this. Okay. This vertex is repeated. So this is not a path. Okay. But it's rather evident what we can do. We can get rid of all this part here. Okay? Okay, formalize. Now we don't have any more drawings. We don't have drawings. We have an unknown graph, and I have a certain path, a certain walk in the graph from U to V. How can we give a procedure to extract a path out of it? And we don't have just one repetition of a vertex. There are 2,000 repetitions because it's a walk which is long 1 million steps with 10,000 repetitions. I want to get out of it a path. How can I do it? Okay, for next time. Oh, this is rather difficult. To show that the number of V, I, V, J walks of length K in G is the I, Jth entry of A to raised to the K, meaning multiply A times A, normal row by column multiplication of matrices. Here, you would need the induction procedure, the inductive proof. Do you here know what an inductive proof is? Proof by induction, it's used quite a lot in these things. Okay for you? What about you? Not so sure? Inductive premise, inductive step? Not so sure? Sorry. It's something very similar to recursion, but it is a proof by induction. You're not. Oh, and from outside, is there anybody who does not know or doesn't feel very sure about proof by induction? No. Outside, everybody knows what a proof by induction is.
It's
No,
like
Professor.
an ordinary proof in which a step must be justified, right?
Sorry?
It's like a normal proof, ordinary proof, in which every step must be justified, right?
It is a very peculiar type of proof because it seems that you are biting your tail. I think that I think I'll do an introduction to proof by induction next time. Okay. I believe that all of you know the binomial coefficients, but I don't really believe that you are so strong on proof by induction. And since proof by induction is needed here, for instance, but it is needed, and also in the next one, but is also needed in many proofs of this course. I'll spend some 20 minutes maybe on the general idea of proof by induction. I'm sorry for the ones who know that well, but I want everybody to know exactly what I'm talking about. Okay? So next time. And so forget about this. Okay? The ones who know the proof by induction you can try that. Proof by induction, if you know what it is, you can use proof by induction for showing this and also for showing this. If G is simple and small delta is greater than or equal to K, then G has a path, has at least a path of at least a length K. Okay? And I suggest for the ones who know the proof by induction, I suggest that you use something which might look stronger, which is this. Let G be a graph with small delta greater than or equal to K. Then at each vertex, sorry, let's do like this without that. Then each vertex of G is the origin of at least one path of at least length K. Okay? This looks stronger, but it is not. And if you want to prove it by a proof by induction, this is the nicest way, I think, to do it. Okay? So there you will see whether you actually know what a proof by induction is. Okay? Distance. I have 4 minutes to give you a very general thing, which is the notion of metric space. A pair XD where D goes from X cross X to the reals, so that for each X, Y, Z in capital X, we have 1 D of X to Y is greater than or equal to 0, and dx y equals 0 if and only if x actually equals y. 2, d of x y equals d of y x. 3, d of x z is less than or equal to d of x y plus d of y z. And this d is called the distance. Actually, what we need for many things that in which we use Euclidean distance, it just needs these three properties, okay? And they are important. In particular, this one, which is called the triangular inequality, okay? And we'll see that in a graph we can have a distance, which is this. If vertices u and v are connected in G, there is a path between u and v. The distance between u and v, which we denote by like this, is the length of a shortest uv path in G. If there is no path connecting u and v, we define this distance to be infinite. Show that if for any three vertices u, v, and w, actually you have the triangular inequality. So this is actually a true distance, meaning duv plus dvw is greater than or equal to duw. Show it by what we have said before about walks and paths. Okay? Okay, so see you tomorrow. Ciao. Could you please talk much louder so that also
Friends, is the meeting finished or?
Oh, yeah, sorry. The microphone was off. I'm answering questions here in class. And if there are questions from outside the class, I'm very happy to answer. Okay, I'm sorry. But the lecture is over. What is your problem with this? Sure.
Do we call this overall, this one, a component?
Component, yeah.
But I'm confused. When I write this, it's not a path, it's a walk. I mean, the vertices are repeated.
What is the question you must answer? The question is, take two vertices. Does there exist a path between these two?
Yes. If
If the answer is yes, then the two are connected. If any two are connected, meaning the existence of a path between one and the other, then your subgraph is connected.
Okay.
Is it maximal among the connected subgraph? This is the other question.
Okay. I think I got confused about the definition of connected.
Yeah, but you know, you are picking up an important point, the use of quantifiers in mathematics. For all, and there exists. Okay? Many here are in terms of there exists. And if there exists one, yours, I don't care about yours, which is not a path. Okay? It's not, are there things which are not a path? Maybe. Who cares? I care only on the fact. Give me any two vertices. If I can give you a path between them, I'm done.
No,
At least
no,
one.
no.
At least one.
Okay.
Okay?
Okay, thank you.
You're welcome. Arrivederci.